All right, welcome back. So this is day 2 of Physics C. We're talking about oscillations, just kind of reviewing everything. So this is all stuff we've already covered, and it'll be a little bit fast. But I'm hoping that we can kind of slow down a little bit for just the proofs, the stuff that was a little bit longer last time. And then if we get through everything, we'll have a long form free response question that we can do. So objectives. This is straight from College Board. I want to derive a differential equation to describe Newton's second law for a spring mass system in simple harmonic motion or for the simple pendulum. Calculate position, velocity, acceleration of a spring mass system in simple harmonic motion at any point in time or at any known position for the initial conditions and known spring constant and mass. Just kind of a big catch-all for use a bunch of our displacement formulas and the derivatives. Derive the expression for the period of oscillation for various physical systems oscillating in simple harmonic motions. We'll take a look at simple pendulums and physical pendulums today. And then calculate the mechanical energy of an oscillating system. So we'll take a look at potential energy as well. Okay, so to start out, if I let x of t be our distance from the top of the piston to this exhaust, so here's my top of the piston here, if I freeze this. Okay, that's the top of the piston, and then the base of the exhaust is right here. So that's where we're letting everything out. Then our function's varying sinusoidally across this equilibrium line. So if this is varying sinusoidally, then we should be able to set this up as a sine function. So here I've got our displacement is equal to our amplitude, our angular frequency, and our phase shift. If this is a sine function, then I should be able to derive it. So if I derive sine, I get cosine. If I derive cosine, I get negative sine. And then with chain rule, I'm multiplying by the omega every time. Okay, so interesting thing here. Well, two things interesting here. The first thing is, once you get down to your acceleration, my acceleration is actually a multiple of what my original displacement was, right?
Yep.
So negative omega squared times my original displacement is my acceleration. I'll be doing more with that in just a second. But you can see that here as well. So my maximum acceleration is going to happen at the ends. My maximum velocity would happen at the equilibrium point. Okay, so if I keep going with this, because our acceleration is really that constant, so negative omega squared times our displacement, and our acceleration is our second derivative, then we could say our second derivative is equal to negative omega squared times our displacement. Okay, then if we bring Hooke's law into this, we can derive a couple more equations. So with Hooke's law, the force of the spring should be equal to negative spring constant times displacement. And our force is also mass times acceleration. So if our acceleration is our second derivative of displacement, then we can substitute all of that in. So here's Hooke's law, force of the spring, Hooke's law, force of the spring. Our net acceleration, mass times acceleration. Or net force, mass times acceleration, mass times acceleration. So force equals force. Substitute for acceleration. And then add this back over to the other side. So if I do add this back over and then divide everything by mass, I get this equation, which says the second derivative plus a constant times itself equals 0. Say that one more time. The second derivative plus a constant times itself equals 0, which we know happens for a sine function. For a sine function, if we derive twice, we end up with negative sine. So that's a second derivative plus a constant times itself should equal 0. Okay, so if I take a look at that, here it is again, what we just found. Our acceleration plus a constant times itself times the position equals 0. So our acceleration, negative omega squared times our displacement, plus the constant, times our displacement equals 0. Okay, and that constant from our last slide when we used Hooke's law ended up dividing by mass. So I'm going to keep that in and just factor out this displacement part. So if I factor out the a sine omega t plus phi from both of these, then I'll end up with this. Okay, so either part of this could equal 0, so that means I can set this negative omega squared plus k over m equal to 0, and then move that omega squared to the other side. So we know omega squared equals k over m, or omega equals root k over m. Okay, so that's angular velocity, omega, k our spring constant, and m our mass. Okay, so I'm going to grab another formula for omega using our period over here. So our velocity is distance over time. Since what's really happening here is our spring's periodic movement is kind of acting in circular motion, right? Which is why I've got these circular formulas over here. So our velocity is our circumference, 2 pi r divided by the period. Therefore, our velocity is also our radius times our angular velocity, or angular velocity is equal to v over r. So therefore I can substitute. My angular velocity then, if it's equal to v over r, should be equal to 2 pi r over t over r, which means our r's will cancel, and I'm left with 2 pi over t. Okay, then I can solve for our period t. So I'm going to multiply both sides by t divided by omega, and that gives me my period of the spring should be equal to 2 pi over omega. Because omega is root k over m, I can substitute. So that's 2 pi over root k over m. I've got a fraction divided by a fraction, so I can flip and multiply. So this will be 2 pi times root m over k is our period of a spring formula. Any questions on what we did? Okay. Then next we'll look at a simple pendulum. So what's going on in my picture here? I've got in blue our velocity vector, which you can see is kind of moving with the movement of the ball. So I've got less and less velocity as we get out towards the sides, and the most amount of velocity as I hit the bottom. Then our acceleration vector is also constantly moving. My acceleration vector is pulling straight up when we're at the bottom, and kind of moving down to the sides when we're out to the sides. Okay, so a simple pendulum is a pendulum that has all of its mass at the end of the string, where the string has negligible mass and the radius is the string's length. Okay, so if all of that is true, then we can start to get our formula for period by looking at our torque. So I've got our formula for torque here. Our torque is our force dot displacement, where our torque is also our moment of inertia times angular acceleration. So if we substitute, our radius right now is our length of the whole string. So if our radius is length, then we can substitute in. My force acting on the ball is mass times gravity at times the sine of our angle wherever it is right now. That angle is changing as the pendulum moves. But that's okay, this equation will still be true regardless of what our angle is right now. So, what angle would we need to have in order for this to just be gravity times L? What angle do we need in order for this sine theta to cancel?
What angle?
Right.
0.
0, okay. So for this swinging pendulum, where would that be?
What?
For the pendulum that's swinging right now, When would the angle be equal to 0?
0, pi, and so on to pi.
Let me rephrase. So this angle is going to be 0 when the ball is at the left, in the middle, or at the most right?
Oh, at the middle.
At the middle. Okay, cool. So we know what's going on. So I've got our moment of inertia, which is ml squared for having all of our mass at the end of that length, times our angular acceleration. So I'm going to divide both sides by our mass, divide both sides by the mass, and I'll end up with, I've got 1L on both sides as well, so I can get rid of 1L. I've got negative g sine theta equals L alpha. Now, as our angle approaches 0, which again is as this mass approaches the middle, is what you said, of this arc, then our sine theta should approach theta, right? The sine of theta approaches 0 as theta approaches 0. So this only works as long as our angle is getting close to the middle, but if our angle is close to 0, then we can resub in here. So I've got my angle here. Negative g theta equals L alpha. I can add this g theta over to the other side to get L alpha plus g theta equals 0, and then divide everything by L in order to get our equation here. Okay, good so far? Cool. Okay, now for simple harmonic motion, when we started, we said our angular acceleration would be equal to negative omega squared times our angular displacement, right? So that's, if we derived twice, I would multiply by negative omega squared. So with this, I can substitute negative omega squared in for alpha. So that's how we got here. Negative omega squared for alpha. So now I've got a theta in every term, so we can divide by theta, and then move my w squared over to the other side, and then take the square root. Gives us omega is root g over L for our simple pendulum. Because by definition, our angular velocity is also 2 pi over our period. So that's our total rotation over how long it takes to repeat. We can set these two equal to each other. So root g over L equals 2 pi over t. And then solve for t. Root g over L equals 2 pi over our period. So if I solve for period, this will be period equals 2 pi over root g over L, right? Period equals 2 pi over root g over L. And then again, I've got a fraction divided by a fraction, so we can flip and multiply. So my period for the simple pendulum is 2 pi root L over g. Okay, just to verify, what is my L?
L is the length of the string.
L is the length of the stream. What is T?
T is period.
T is the period. Can you give me another word for that? Or explain what the period is?
It's time taken for one rotation.
One rotation, you're right. So for this simple pendulum, what would one rotation mean?
Simple. So going back to other side and then come back.
Right. So I have to get back to the same point that I was before. Okay, cool. All right. And okay, we can also have a physical pendulum. So physical pendulums are a little bit trickier. It means not all of the mass is at the end of the string. They could be in any form. So it doesn't have to be, I think everything we've seen so far has been a uniform rod. It could be something crazy like this, where we'd have to find the center of mass ourselves first. The key to a physical pendulum is that they rotate according to the center of mass. Okay, other than that, we're pretty much the same. So I'm going to start the same way we did last time. I don't think I can move that, but this first line says FR sine theta equals our torque.
It's not been showing here.
Sorry, say one more time.
It is not showing in the screen right now.
Okay, you've got a blank screen right now?
No, it's simple pendulum screen.
Okay. Let's see, why don't... I'm gonna quit and then I'll call you back and we'll see if that helps. Okay. Hello again. Oops. Hey, so I think that was my end. My Skype just crashed. So I'm gonna try one more time. Okay, can you see now?
No, wait.
Okay, I am showing broadcasting on my end. Okay, if you can't see, I did send all of the PowerPoints through WeChat. So why don't you pull up the PowerPoint on WeChat and we'll just keep going from there. We're on the slide that says physical pendulum. Okay, let me know when you're ready.
Yep.
Okay, cool. So first line up at the top, our torque is Fr sine theta again. Our torque is also our moment of inertia times our angular acceleration. So we can substitute. In this case, though, our radius is not just our length, because our center of mass is at half of our length, right? So my radius right now is L over 2. Okay, other than that, we've got almost the same math that we did last time. So as our angle approaches 0, the sine of our angle is going to approach our angle again, so I can substitute theta for sine theta, and then simplify. So I'm going to add this negative mg L over 2 theta to the opposite side, and then divide everything by our moment of inertia. Okay, so that gives me my last line in black there in the middle. My angular acceleration plus mg L theta over 2 moment of inertia equals 0. Okay, again for simple harmonic motion, our angular acceleration is negative angular velocity squared times angular displacement. So we can substitute for our angular acceleration. Anytime that I see an angular acceleration, I'm going to replace it with negative omega squared theta. Okay, then I can add that back. So this will be mgl theta over 2I equals omega squared theta. Okay, my thetas on both sides will cancel, and I can take the square root of both sides to get omega is root mgl over 2I. Good so far?
Yep.
Okay, then omega is also 2 pi over t, so we can set these two equal to each other, so therefore if I rewrite this, this is t is 2 pi over omega, t is 2 pi over omega. Substitute for omega, omega is root mgl over 2I, and again I've got a fraction divided by a fraction, so I can flip and multiply. So this is 2 pi times the square root of 2I over mgl. You may see this written differently depending on what textbook you use. Some textbooks use d for a distance that is L over 2. So if I did that substitution, then this L over 2 that you see here would be replaced with d, and that would end up on the bottom of the fraction. So you can see that on the bottom left. 2 pi root I over mgd is the same thing, but d is L over 2. All right, any questions on physical pendulums?
No.
Okay. Once again, what is our L for this problem?
L is the length from the end to the center.
Not the length from the end of the center, actually. L over 2 is the length from the focal point to the center. So what is L total?
Just length from the end to the other end.
Right, so L is just length from end to end. Okay. Next slide, energy. Can you see from the stream yet, or looking from the PowerPoint?
Looking from PowerPoint.
Okay, cool. So, as you can see on this sine function, as we keep going up, so we get further and further away from equilibrium, when we reach that crest of the wave, so that's the highest point of the sine wave, our speed, our velocity becomes 0, right? We know that because our piston that's moving changed direction from going up to going down. So if our velocity changed from positive to negative, then at that point we must have been 0, right? If our velocity is 0 and kinetic energy is 1/2 mv squared, then our kinetic energy also has to be 0 at that high point. And if our kinetic energy is 0, then we should have the maximum amount of potential energy at that high point, right? Okay, same idea for the trough. So at the low point, our kinetic energy is also going to be 0 because we changed from a negative velocity to a positive velocity at the bottom there. So if that's true, then our velocity should have been 0, and if our velocity is 0, then our kinetic energy is also 0. Therefore, we've got our maximum potential energy at the bottom of the wave as well. At the equilibrium point, so that's at the center line, the opposite is true. I should have the maximum velocity and the minimum potential energy. Okay, starting with Hooke's law, I've got our spring force is equal to negative spring constant times our displacement. So because our definition of work is force dot displacement, we can integrate our force in terms of our displacement in order to get our work, right? So I'm going to integrate from position 1 to position 2 of our force in terms of displacement. My force is negative kx with Hooke's law, so I can substitute that in. And that way, if I integrate, this is just power rule. So I'll add 1 to the power and divide by the new power. Gives me negative kx squared over 2. Again, k is a constant, so we don't have to worry about it with our integration. No integration by parts or anything. Okay, then I can substitute. So my upper bound minus my lower bound would give me what I have on the bottom. My signs may look a little bit weird, but I had a negative on the outside there. So this is negative for my upper bound and then negative for my lower bound, but I would have subtracted there. So that's a negative. Negative is positive. Okay, so my work is negative kx2 squared over 2 plus kx1 squared over 2. Okay on that step?
Yep.
Cool. Now, by definition, my change in potential energy is my negative work, right? I will lose the work that you need to do in order to create some potential energy. If you're going to push a spring off of your equilibrium point, the you would lose the energy that you need in order to push that spring that far, right? And that energy would be how much potential energy you gain. So by definition, my potential energy is my loss of work of the spring. So therefore, I could just change the sign here to get positive kx squared over 2 minus kx1 squared over 2 would be my change in potential energy. So if we said that our potential energy was 0 at our first position, so that means we started at the equilibrium point, then my potential energy of the spring relative to equilibrium would be kx squared over 2, where x is our displacement from equilibrium. Any questions on how we got our energy equation?
Nope.
Okay. Can you explain why, if we had an ideal simple harmonic motion system, our energy would be conserved?
Energy, yeah.
Okay, can you explain though? So how is our energy being conserved right now?
There are two types of energy. First one is kinetic and the other one is potential. So at the end point there is maximum potential energy but no kinetic energy,
Okay.
and at the other end as well, and then in the equilibrium point there is maximum kinetic energy but not potential. There is no potential energy, and then between those 2 points there are some kinetic energy and potential energy.
Okay, cool. So if we were an ideal simple harmonics system, so that means we're not losing any energy due to friction or anything, then all of my potential energy is constantly converting back to kinetic energy once it reaches equilibrium, and then back to potential energy when it gets to a crest or a trough, and then back to equilibrium again, right? So all of the energy in the system would be saved. Okay, in the real world that doesn't happen. What are we losing energy to?
Sound, friction, maybe heat.
Awesome. So all of those are good. Okay. So I am going to stop there. I want you to complete all of the multiple choice questions that are in drill 11. And then I want you to complete free response number 1 and free response number 3. I was going to do free response number 2 with you today, but since the stream isn't working right now, I'm going to try to start with that on Friday.
So 1 and 3.
Yep. So we'll complete free response question number 1 and free response question number 3, and then all the multiple choice questions in that drill 11 packet.
Okay.
All right. Thank you very much for coming. I'll see you Friday.